Okay, let's continue again. In case of dynamics of single rigid body, we can use Newton-Euler formulation and Lagrangian equation, Lagrangian formulation. Actually, Lagrangian formulation we already explained. In case of Newton-Euler method, there is a equation. This kind of things. So actually, this one is I plus 1 and I. Yeah, this one is I indexed, and this one is I plus 1 indexed. So if you're starting from I equal 0 to I equal n, then you can find some velocity component from 0 link to n link. And then if you calculate velocity component, and then you can calculate force and moment from end to base. So there is two kind of iteration. First one is I equal 0 to n-fold iteration. In this iteration, you calculate velocity and acceleration. So we call this one is velocity propagation equation. And then after finished fold iteration, you have to do inverse iteration from n to 0. In this stage, you calculate the force and torque. So this is Newton-Euler formulation. So in this time, we will apply this kind of method to the, there is some error. Okay, I will relearn one note. Okay, I will apply this kind of formulation to the twist. Actually, in the key factor in modern robotics class is to deal with the rotational movement and translational movement together. So this one is omega, about this one is indicated, described by omega, and this one is described by v, linear velocity and rotational velocity. And to describe these things together is twist. So let's starting from the original equation to the twist style equation. Firstly, if there is some rigid body, mass is m, and there is B frame in the center of mass, and there is some trajectory, which is P. And this P dot can be calculated by VB, linear velocity, plus omega B. This one is rotational velocity cross PI. So this one is general equation of rigid body, single rigid body. So if we take the time derivative, here, why this one is not? Then we can calculate P2 dot. And this one becomes like this. And here, because there is cross product here, we should use chain rule. So firstly, take the time derivative about this one and plus take the time derivative to here. So we can calculate like this. And if the pi is equal to center of mass, like this, so we change it pi with the ri. Then this pi to that become ri to that, and the equation becomes like this. And this one is linear acceleration. Linear acceleration equation. And using this linear acceleration equation, we can calculate force. And force is ma. So we can multiply the mass here. And in the case of torque, in the modern robotics textbook, we usually we use M symbol for indicate torque. Torque, sometimes we call this one is moment. So using this M, so we describe the torque, M equal R cross product F. So the cross products can be changed to the skew symmetric matrix. So in here, we introduce the new concept, which is length. Length is indicated by large capital F symbol, and this B indicate body frame, and this range is some vector, not some vector, describe together the moment and force. Actually, as I already told, in modern robotics class, we describe rotational movement, translational movement together. So the twist is also like this. So rotational, translational. In case of force, we indicate together moment here and force here. This one is linear thing and this one is rotational thing. So if there is multiple body, multiple rigid body, we can sum like this. And let's see this one. If because the R is center of mass, the center of mass is from the meaning of the center of mass, it is basically m multiply r. Sum of r m multiply r becomes 0 because this one is center of mass. So we can make this kind of equation because m is scalar value. Even though we take the skew symmetric matrix here, it becomes 0. And also we will change this equation. So from this equation, let's start here, and this is here and this is here, and this equation like here, and this equation is here. And using this relationship, we can simplify this equation. Firstly, this and this go here, and this equation, in case of this equation, we can use this relationship. So if you're using this relationship, these two things change the position, and because this one is 0, this term is equal to 0. And about this term, we use this calculation. So omega b symmetric square like this, and change the position of these two things and take the minus, and we take the change the position and take the transpose like this, and then we take this relationship transpose and minus is changes like this, and it becomes like this. So this equation changed like this, and then also this term equals 0. So these two things becomes 0. So simply this part is limited when the R is center of mass. So the sum of the mass becomes just M. So the equation FB, the force of body frame, becomes very simplified. And also similar thing is done the moment term. In the moment term, this M cross product, R cross product F. So this equation is R2 dot, and this by using this simplification, we can write this equation. And here, the IB is equal minus sum of mass I and R symmetric square. So this one called rotational inertia matrix. And here is I, here is I. So I omega dot, I omega B dot, and omega B symmetric I B omega B. So moment equation also very simplified. And that's it. So the Newton-Euler, the classical equation in the Newton-Euler method, which is this one, when the rigid body, when we deal with the center of mass position, and if we derive the equation of range, it becomes very simplified, like this and this. So as a result, we can see the twist range formulation. So simply, the moment M equal IB omega B dot plus IB twist IB omega B, and FB equal M VB dot omega B symmetric VB. So if we describe this one as matrix form, we can stack together like this, MB, FB, and this one is, we already call this one range. Range B equal the rotational here, rotational inertia matrix IB, and this I is identity matrix to describe the M, and this multiply this one becomes this one, and this multiply this becomes this one, and this multiply this one is this one, and this multiply this becomes this one. Actually, this VB skew symmetry is not necessarily, because when we calculate this one, actually this one is not important. But the reason we describe like this is I will explain later. And the relationship transpose n minus, we take the transpose here and take the minus here. So the length equal moment force and this equation. And also we can naming each matrix. Firstly, this one is spatial inertial matrix. So we usually using GB. This symbol is not exactly same with G or G, but I recommend you to see the modern robotics textbook, and the symbol like G, which is spatial inertial matrix, and there is rotational inertial matrix here, and there is mass matrix. And this one is twist time derivative of twist. So it is like this. And this one is also G. This one is twist. And this one is a new concept. So this one is new concept. We learned about the other joint. So there is a capital A other joint. In here, there is rotational matrix, and P. This one is actually P cross product R. So this one is something like that. Similarly, this term we call this one as small other joint. So this one is large other joint. In this case, this one we call this one is small other joint. Actually, there is large SO3 and small SO3, and large SE3 and small SE3. Similarly, there is large other joint, and there is also small other joint. And in this case, we use twist here, and here we use T. This one is different thing, and we call this one Lie bracket of twist V. So actually, we added this symbol here, V symbol here, because this one is physical meaning as small other joint. So this wrench equation becomes wrench B equal GB multiplying twist time derivative of twist and small other joint which is we call leave bracket of twist B, and then GB twist B. So finally, this equation is dynamic equation for single rigid body. And this one is very simplified form. So as a result, we found dynamic equation which can be used in modern robotics style. So in here, the important thing was other joint, small other joint. Actually, in rotation, there is large SO3. It can be transform small SO3 and large SE3, and also it can transform small SE3. Similarly, large other joint can be converted small other joint. So this one is very, very important. And also, there is other joint map. So using the other joint, we can convert the twist from S frame to B frame. Similarly, if there is A frame and B frame, there is this kind of relationship. So using this relationship, we can convert some G matrix, which is spatial inertia matrix. So this one is indicated in B frame. So if you want to transform this matrix from B to A frame, we can use this large other joint relationship. So this relationship came from the rotational energy. Actually, rotational energy can be calculated using twist multiplying spatial inertia matrix. And even though in A frame and B frame, this energy is same. So using this relationship and the other joint map relationship, we can calculate it, the transformation method. So if you want to transform some GB to GA, we can use other joint transpose of other joint and other joint here. Okay. Okay. In this time, we learned about dynamic equation of open chain robot in modern robotics style. So in modern robotics style, actually the equation is very simplified. In the Newton-Euler equation, actually the equation is very long, and actually if you use this Newton-Euler equation, the hand calculation is very, very difficult. But in the case of using program, you can program this equation as code, programming code. And if you take the if you're coding this kind of forward iteration and inverse iteration, you can systematically calculate the dynamic equation using Newton-Euler formulation. Actually, in my GitHub, the intelligent robotics library, you can check the Newton-Euler equation. But Actually, in modern robotics style, we describe rotation and translation together. And in modern robotics style, we simplifying the equation very, very simply. So all these long equation becomes very simple matrix form. And even though this matrix form also named, and it becomes very simpler equation. So actually, this one is final equation, and this equation describes linear force and rotational moment. So this is the power of modern robotics library. So in the next class, I will explain more detail, and I will give some example to use the modern robotics library to calculate dynamics. Before finishing the class, we have to think about the schedule of final exam. Actually, uh, in my previous announcement, I uploaded solution of chapter 3, 4, 5. So the final examination will came out from chapter 3, 4, 5. Yeah, actually, I want to take an exam from the dynamics, but the hand calculation is very difficult in dynamics. So when you calculate or when you're using dynamic equation, you have to use the programming code. So actually, it is impossible. I think it is impossible to take an exam about the dynamics. So the only the range of the final exam is limited to the chapter 3, 4, 5, and about the time, it might be good to take an exam the Thursday. But the day of the final exam, I will announce in KakaoTalk, and I will make a day. Okay, I will fix the day of the final exam. But I think the next week will be the final exam. Maybe Thursday will be the final exam day, and we will take the exam in the similar way with the midterm exam. So thank you.